It comes up all the time in science fiction, and I get asked about it. And you know what it is? It's wormhole. The day we have wormholes, you won't need airports.
In the enigmatic tapestry of spacetime, where curves and stretches weave secrets and time itself contorts into mysterious dimensions, we find the gateway to countless enigmas. Amidst this cosmic riddle, an alluring enigma beckons, the enigmatic wormhole. As we traverse the realm of manipulating space itself, we are drawn into the captivating quest of crafting a bridge, transcending the boundaries between our present sanctum and a distant enigma. But as we venture deeper into this labyrinth of wonder, a shadowy inquiry unfurls. How shall we forge this transcendent passage, and what essence of matter and energy shall become the keystones of our endeavor? Herein lies the cryptic response, concealed within the cryptic equations wrought by Einstein's mystic hand. These equations, a cipher to the uninitiated, unveil the specific attributes requisite for the crafting of this ethereal bridge. Yet, within this grand enigma, an ominous challenge emerges. The very matter and energy required in their nature yearn to collapse, veiling the practical realization of these cosmic conduits in an aura of uncertainty. In the deepest shadows of this cosmic riddle, the enigma of quantum wormholes lingers, casting its enigmatic veil over the quest for answers. This is Reveal the Mystery. If you are curious to learn mysteries of the world, space and beyond, consider subscribing. All of matter, understanding all the stuff that makes up our world, is a pretty tricky business. You see, everything from tiny particles to big elements can be broken down into a simple list of its most important traits. Let's take electrons as an example. These little guys have a certain weight, a specific way they spin, and an electrical charge, and that's it. No more fancy characteristics. All electrons are pretty much the same when it comes to these traits. This list of traits is what we call information. It's like the ID card for every particle. Now, the cool thing is that this information isn't just about individual particles. It's also about how they interact with one another. We believe that keeping track of all this information in the universe is super important. We can't let any of it disappear. If for some reason an electron loses its unique traits, like what would happen if it fell into a black hole, it would mean that we've lost information from the universe. This idea goes against the fundamental rules of physics, where we always expect to keep this information safe and sound. The discovery of black holes. Imagine stumbling upon a place in space where everything, even light itself, gets trapped. That's a black hole. Now, when people first discovered black holes, they didn't really think they were a big deal when it came to losing information. The thought was that all the info was hidden behind an invisible wall called the event horizon. So, any data that fell into the black hole stayed hidden, and we couldn't see it. This gave us a sense of relief, believing that information wasn't lost. However, things got a bit more mysterious when Stephen Hawking, a famous scientist, started poking around. He started looking into how things work at the tiniest levels, like the realm of quantum mechanics. You can think of quantum mechanics as a place where even seemingly empty space is buzzing with activity, kind of like a party for tiny particles. Stephen Hawking's contribution. Hawking's big revelation was that black holes can do something special in this quantum party. Imagine that particles are like dancers paired up in twos. In the normal dance, they always have to stay together, but sometimes one can sneak away and leave the other partner behind. What Hawking realized is that black holes can make one dancer disappear behind their event horizon and leave the other one outside. This escaping dancer comes from the quantum party in space. Now imagine you're far away watching the show. You'll see this escaping dancer and think, hey, the black hole is emitting energy. So according to Hawking, even though nothing from inside the black hole escapes, the black hole still appears to give off energy because of this special quantum dance. But here's the twist. As this escaping dancer goes away, the black hole actually gets a bit smaller. Over time, Hawking calculated that black holes would completely evaporate, like they're burning away. This opened up a big puzzle. If black holes disappear, what happens to all the information that fell inside them? This question gave rise to what we call the information loss paradox, a real brain teaser in the world of physics. Holography. Think of holography as a whole new way to look at black holes. Instead of picturing them as these giant cosmic objects with a hidden interior, imagine them as something more like a magic trick. It's like having a flat, two-dimensional piece of paper that somehow contains all the secrets of a three-dimensional world. When you shine a specific light on this piece of paper, it makes a 3D image pop up, kind of like when you watch a hologram. This concept was first brought up by a scientist named Lenny Susskind. He suggested that maybe, just maybe, black holes are not as we see them. They might be more like 2D drawings of 3D objects. This new way of thinking has some pretty big implications. It means that all the information about things falling into a black hole might be stored on the surface of the black hole. And when the black hole eventually disappears, this information is still there, encoded in the stuff it spits out, which can help solve the problem of information loss. Firewalls. Now, here's where it gets a little crazy. The idea that all this information is just hanging out on the surface of the black hole can lead to something called a firewall. Imagine you're brave enough to cross the event horizon of a black hole, and instead of finding a quiet space, you encounter a blazing hot wall that instantly obliterates your existence. Yikes. This idea shook things up quite a bit because it goes against what we thought we knew about black holes. You see, according to Einstein's theory of general relativity, there shouldn't be anything dramatic happening at the event horizon. To avoid the whole firewall drama, some scientists suggested a different approach. They proposed that the information outside the black hole is connected or entangled with the information inside it. It's like two dancers who can only dance in perfect harmony. If one spins left, the other spins right. So, by looking at the dancers outside the black hole, you could figure out what's happening to the ones inside. This could help us understand what's going on without needing a fiery wall. And if things never fall into the black hole, it's like the dancers outside are dancing with themselves, which is pretty weird. This idea even hints at the existence of quantum wormholes connecting the inside and outside of the black hole. These concepts raise a lot of questions and offer some potential solutions to the puzzle of information loss. A metaphorical perspective. Okay, imagine understanding black holes as if they were more like a beautiful embroidery. Instead of thinking of them as a solid, impenetrable thing, think of them as a complex weave of threads. These threads overlap, creating the illusion of a boundary, like the shadow of an object. However, in this metaphor, the overlapping threads are like the hidden pathways or quantum wormholes that allow information to travel between what goes into the black hole and what comes out. This perspective tells us that the event horizon, which we thought of as a solid surface, might actually be formed by the interactions of these quantum threads. In a way, it's like a cosmic embroidery, and these threads are like the cosmic stitches that define the event horizon. In the end, the journey into the world of black holes, information preservation, and cosmic mysteries is filled with many intriguing ideas, from wormholes to holography and firewalls, all of which could reshape our understanding of the fundamental nature of the universe.